Now I want to say a word or two about distributive law. One is that I forgot to give you the reason why it's true. For all numbers L. Now we talked about already how among all these laws that this is the one that most misunderstood, most we feared a little bit. But you just this is the. So let me even before I tell you explain why this. We want to emphasize this law for at least two reasons. One is the thing we've been talking about. It's not well understood and it's not used sufficiently. And therefore, whenever that happens, you want to make a point of saying, learn it, 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 right? But there's something beyond that. This is, in some sense, the most critical law for numbers. You know what? Okay. Yeah, okay.
I guess you can, if you use it properly, you can do a lot of shortcuts in your computation.
Yes, that's true. That's true. Gary, you want to say?
I was going to say it's like the thing, it's what holds multiplication and addition together.
Yeah, that's a more fundamental reason. The shortcuts are nothing but manifestations of this one fact. You see, when you do not computation, what are the two operations you look at? One is addition, the other is multiplication. Now, some of you are going to say, "Oh, we have subtraction, we have division, right?" But so one of the things we're going to show you that. After a while, they don't count. Division is nothing but multiplication. Namely, 5 divided by 2 is the same as 5 times 1/2, right? And subtraction is nothing but addition, meaning that 3 minus 5 is nothing but 3 plus negative 5, right? So these are the only two operations that matter to us. So you have the two operations operating at the same time. You think they can be randomly assigned, right? That's what you think. I can do addition any which way I want. I can do multiplication any which way I want. No, right? It's not true. It's not random. Once you decide on what addition is, your meaning of multiplication is not completely determined, but you have to be very careful. Why do you have to be careful? Well, because you don't do it right, it's not going to hold. These ties should get together. That's why the distributive law is something that you should pay serious attention to. Right? So, I want to bring that up. Now, what we want to believe is? Well, maybe since I've given you a lead, maybe you can tell me why this is true. That you would like to believe it. Do you want to?
Using an area model?
Yes. Yeah. What is L times? So M. And so N plus N is what? Concatenation, right? So what's L times M plus N? Well, that's the big rectangle. The area of the big rectangle. Now, is L area here is L, that one is L. So the left hand side is nothing but the area of the big rectangle. Now what about right hand side? L times M, well, L times M is what? This rectangle, right? this why this kind of picture is impossible to draw. Right now I have to pick up an arrow because I don't know which arrow it is. L times n is an addition, of course, putting two areas together, which, as you know, is big rectangle. So that's why it's reasonable. Again, this is the argument we're going to use for fractions. Exactly same thing. So for fractions, the distributive law always also holds. Okay? Are there other questions about the distributive law? Now we'll be using it right and left, so don't worry about it. If you say, "Oh, we haven't used it yet," well, no, you're get sick of it. All right. Okay. Now we come to the exponents. Well, not only that, but you see, I'm going to up the ante. Last time I gave you something not very big. I'm going to make it very big. I raised this question, right? And I didn't answer it. And now, of course, I have every intention of answering it. So I ask you, why is this true? You all know it, and take for granted. But now you really want to convince yourself that it's right. Not just because other people told you it's right, but that you know that it's right. Of course. Yeah, you don't realize. To explain why this is right, you need the distributive law. You see. That time, take the trouble over you. And also, of course, I didn't finish it, but that's beside the point. All right, so keep this in mind. Whatever I say, at least in the short term, in the back of my mind, I want to do this. Right? So now let's pick up the loose threads, the loose ends. Remember last time we talked about this in 100? Remember this? Now the real statement of this is what? 10 plus 10 plus 10 plus 10 plus 10, 10 times, give you 100. And the reason I know that was just keep counting. And every time you count, you are adding, right? Addition is nothing but count and count and count. Right? That's addition. So it's a statement about counting. No question about it. Huh? Also, we have this too. Skip count by 100. Skip count 10 times. I convince you, I hope, that you get to 1,000. 10 steps. You get to, oops, sorry. 110 get over 10%. All right. Now we're going to build on this. But you know, but by the way, look at this. Why do we want? Look at this exponent. This is okay. Once in a while, I hanker after whiteboards because whiteboards give me a lot of colors. I can't use it. Or even the red chalk I cannot use basically because once I write on it I cannot use it. Well, okay. Look. This, you see, I know to look at it backwards. Instead of saying 10 times 100 is 1,000, this is really the statement of what? 10 plus 10, times 10 is 1,000. That's it. Right? Now I remind you again, when I write this, I don't need to tell you how you take the multiplication. Remember, given any number of numbers, any collection of numbers, I want to multiply them, any which way I want, the end result is the same. Right? So, do it any way you want. So, replace the 100 by this, this. Right? Now, let me keep going one more time. Now, you also know that 10 times the same reasoning tells you if I skip count by 1,000, starting from 0, same reasoning tells you what? You get to 10,000, right? Take that. 1,000, 2,000, 3,000, 4,000. 9 steps get to 9,000. Another step, 10,000. Right? That's how you go from the 4-digit numbers to 5-digit numbers. Again, I play exactly the same game. I just found out that 1,000 is what? This one. Right? Therefore, this is really the statement of what? 10 times 10 times 10 times 10 is equal to 10,000. Good? Now you believe me at this point, right? I'm going to keep going like this, step by step. What am I going to end up with? I use 10 times 10 times many times. How many times you want? 5,000? 300,082? No loose talk ready. It cannot be thrown. What do you suggest I do? I want to say no matter what it is. You use a symbol instead, right? And so say, oh, take any number you want. Keep backing. You just say, let there be n such factors. N times. Where n is a positive, a non-zero whole number. Do that. Now I want you to tell me what should I say. Look at the examples I've given you. What do you think I should say? What is the right conclusion? It's what? Equal to what? 10 and then what? Huh? What? No. What number? What do you think? What's the correct number here?
10.
Oh, no. I don't know what that means. You're jumping to conclusions, right? I'm not going to do that. I'm not going to say something that you don't know.
You're going to have n zeros. 1, 0.
N zeros, right? You have to have 1 followed by n zeros, yes? Why is that? Well, look. You have 2 factors, 2 zeros. 3 factors, 3 zeros. 4 factors, 4 zeros. It's not as if I have to stop. I didn't have to stop. Okay, keep going. We can spend a whole day doing this. Right? 5 factors, 5 zeros. 6 factors, 6 zeros. Therefore, no matter what n is, n zero. Now I'm showing you several things all at once, by the way. One is, why do you use symbols? Well, the answer is, if you can say this without using symbols, let me hear it. What do you want to say? Can you? Can you say it without symbols?
Sounds elegantly, but you
Yeah.
can do it.
Well, not as elegantly, but try to say it. Try to say it. Try.
So
Yes?
if you're going to say however many number of times you're multiplying 10 will be the same number of zeros after the one on the other side.
But you see, you're using numbers
Yeah.
in this way where you are just at the listener's mercy, right? You hope to God that he actually believes you.
No.
You're using the same number, right? That's not very good.
No, I agree.
Exactly, right? You want accuracy, you want clarity, and you want, above all else, in mathematics requires brevity. You can compress, the more you can compress in as few words as possible, the more you want to do it, right?
Yeah.
So that's why you use symbols. So in case you see why for example, why you say n times n equals n times n is committed, all that because otherwise I don't know how to say it. The same thing, this is an introduction to the thinking. By the way, using symbols, this is now routine. Every school student knows how to do it, or has to do it. The use of symbols like this, it's like the Hindu-Arabic numeral system, was not accepted until 1600. Mankind went through at least 16 plus 4, that's 2000, isn't it? I mean 20, so 2000 years. During the 2000 years before 1600, when mankind was, or people kind was engaged in serious mathematics, no one knew how to do things the right way. So we all quadratic equation now, now, no matter what, you must remember this thing, right? Ax squared plus bx plus c. Does everybody remember this? The looks of it, everybody. This, every 7th grader writes down, whether he or she understands it. He read it, right? But nobody before 1600 could write it down. Only about around after 600. They would say what? They would say, if they want to explain something about this, they say, look at this. Look at this again. Look at something else again. Oh, look at another one. And then you say, you see what's happening? You see what I'm doing? Whether you see it or not, you have to go on because you can repeat all possibilities, right? Infinite number. That's what they used to do. This is Arabic algebra. The Arabs, the Islam mathematicians, have made a very important contribution to mathematics by introducing such considerations. But they had no symbols. And that's all they ever did. Basically, in fact, they didn't even do this. You know what they would say? I forget the exact name. Roughly, it's not entirely correct. Right? Take a number, multiply to itself, and multiply 5. And then add to it 3 times its size. And then add 1. Look at this. And then you go on. What you want to do, you just keep going like this. The next time you say, look at a number. Multiply to itself, then multiply 15. Add to it 7 times its magnitude. And then that's 8. And so keep going like this. Long paragraph. It's unbearable to read. This is 9th century. But that's the beginning of algebra. Very modest beginning. So from 8th century to about 800 to about 1600, 800 years, people were writing this right. Towards 1600, people began to see that this was no way to go. And then they started to have some mangled versions of the symbolic notation. Eventually, by 1600, actually about 1640, then they settled down on some way of writing it reasonably. That to the Descartes thing. The long development, but the main person had to push it over the hill. Okay. That's the person also who co-discovered analytic geometry. Same person. Anyway, so that's long and short of this. Alright, so we have this one all-encompassing formula. You multiply it n times, the number you get 1, 0, 0, 0. Now, as I was trying to explain to you, it's not just that mathematicians like to be brief. You do too. Would you like to write this all the time? And then curly brace n times. You want to do that all the time? Yes or no?
No.
Good. So now you agree. We have to find a notation for this, right? And that's the notation. The notation, shorthand notation with this is 10 to the n. Because it's too long. That's the origin of the exponent notation, exponential notation. Right? Agreed. Now, this is a definition, by the way. This is a definition. Another one, don't ask why. Right? Kelly is called Kelly, no reason. Just because she's called Kelly. Just you agree. Or your parents agree. I don't think. So agreement is what we call definition. Is usually just an agreement. You don't have to give a reason. You know why you don't have to give a reason? Because if it's no good, nobody uses it. That's the end of it. You see, mathematics in that sense is democratic. In some other ways, not. But this is democratic. So we agree to say that instead of writing this whole mess, we just say 10 to n. Then once you agree to that, this whole equality, this whole theorem, now is telescoped into one single fact. 10 to the n is equal to 1, 0, 0. Now I want to say a word. You see, I keep saying no definitions. Know your definition, right? And then sometimes you see me put something on the board and say, that's theorem. Now I want to make clear, at least you know what is the difference between the definition and the theorem. A definition, as I just explained, it's just gentleman's agreement, or rather, yeah, that's not right to say it these days, right? It's a people's agreement. Disagree. When you say something's a theorem, that means what? It's on the basis of the definitions, on the basis of mathematical reasoning, we arrive at a conclusion. And you call that conclusion. No matter what it is, you are entitled to call it a theorem, if you want. So a theorem always involves a process of mathematical reasoning. Not agreement. In other words, the theorem is true, whether you like it or not. No democracy. Alright? And that you can agree. It's not democracy. It's not a democratic. You don't get to vote on this. Yeah? It's true. Period. So now, in case you get seduced by the notation, let's say what it says again. I'm saying is what? You multiply 10 to itself 10 times. The number you get is a number which begins with a 1 followed by n0. Right? Now that, I don't think you say it's obvious. Is it? Is it obvious to you? I hope you don't think it's obvious. It's not. You know why it's not obvious? Okay. All right. Let's see. You all think it's obvious or not? When you don't say anything, that means there's a rumbling of discontent, I think. Well, you know why it's not obvious? Let me try this.
Yeah.
Oh, yeah, let's do that. How many of them? Yeah, let's do this. Let's do
The
this.
clicker.
Oh, no, thank
You
you.
ever done a clicker?
One, this.
I did that yesterday.
It is obvious. Two, it is not. I'm not yet someone of the 21st century, so I don't think of, but I will be that. Every time I want to answer your question, I'm going to think of the figure. Three, maybe. In other words, you're on the fence.
Are you asking if it's obvious that
That
it's
this
a
is true.
theorem? Or that, okay, that the theorem is true?
You say, oh, yeah, it's obvious.
After we look through.
And for those who say it's not obvious, I like this. Well, of course, I cannot use a clicker, but you'll be ready with an example why you think it's, it's obvious.
Can I ask a question?
Yeah.
I'm a little confused. Is this right here a definition or a theorem?
This?
It's a theorem.
That's a
because
theorem.
The definition has been
The definition is for this notation, 10 to the
just a
n.
notation. That's the definition. But
Yeah.
this right here, this is a theorem.
Yes.
Thank you.
Okay, so are you
I had
ready?
trouble with this one. I got about half response earlier.
Oh, everybody's on the
I thought
fence?
they were, no, I thought they were still thinking.
Okay.
Okay, I thought we were.
Well, I clicked when I started. I said it wasn't open.
It's open now. Yeah.
I just forgot. Go back and do it. Really?
Okay, so I'm gonna call it. I think everybody's done this.
Okay. Hey, that's pretty good. That's pretty good. Look. Wait.
So you have a lot, that it's not gonna be.
No, I could not. See it? You see it? That's a good distribution. You guys have done things honest. Right? That's good. Yeah, that's good. That's good. Well, okay, for those who say it's not obvious, why do you think it's not obvious? Yes?
I think it's not obvious without that middle process that we went through.
Right. Well, then we
I
start
mean, we
with
had
10
that
times 10 is going to 100, 10 times. Well, you see that, then
That
you begin
is-
to understand. Let me give you another example why it's not obvious. I'm going to give you another funny argument why it's not obvious, right? If it's really that obvious, you expect the following, okay? Take number 5 instead of 10. You think 5, 10 is equal to 5, or whatever. You think that's going to be true? See? Whatever, just take any other number. It is peculiar to 10. So if there's something peculiar to 10, it is not obvious. Why? Because if it's obvious, then it should be true for everything. Right. Now we're in business. We can do this. One more thing and we can do this. All right? Well, once with this notation in place, now we look at place value again. But now we are going to talk about place value. It's not good enough. Meaning that place value is not just something you talk about. In mathematics, if there's something you want to say, you normally can say it completely explicitly, but no room for doubt. So let's look at number 5, 7, 6, 1. We say that 5 stands for 5,000, 7 stands for 700, 6 is 60, and 1 is 1. Not good enough. We should be able to say it more clearly. Well, okay, let's look at this. Now you have to remember what addition is, right? Addition is counting from 0 and keep counting. Look at 5. What do you locate this number? Well, you remember how counting is done. You write a list of all 4-digit numbers. The first row begins 0, right? Second row is 1. Third row is 2, 3. Anyway, I'll run out of space. 5, 4, 5, 5. Right? So, of course, the first number in this row is 5,000 because 4 digits, right? So you start from 0, you count. Right? So lots of windows like this. You count. When you get to here, you've counted how many times? 5,000 times, right? So to get here, you start you count the steps to get there. But before getting there, you pass through 5,000. Record it. Now you continue. Of course, you're not there yet. Keep counting. Now you keep counting, that means what? You're adding, right? Get that, right? You want to get to 5761. You keep counting from 0, and then you pass through 5,000 first, and record that landmark. What do we call it? Now you keep counting. Now what will you do? You're counting within this one row. Within this one row, that every number begins with a 5, which to us now is irrelevant because just that was a label we put it on, remember, right? So we all now look at how many more steps you want to count before you get to 761. That's the thing that matters, isn't it? So now we look at 3-digit numbers and say you started with 0, 0, 0, right? Which used to be 5000, but we ignore that. So you list all the 3-digit numbers, right? You say you keep counting like this. When are you going to land at 761? Now, 3-digit numbers. The first row begin with 0. Second row begins 100. Third one is 200, 300. 400, 500, 600, and 700. Right. So you keep counting, and you have to keep counting 700 times more before you get to 700. Correct? Again, we'll record that landmark. And 761 is somewhere here, in this row. Correct? Therefore, the same reasoning says, well, everything is 7 something, forget it. Just take the last 2 digits. I repeat, right? Here, everything begins with the 7, so the 7 means nothing. You're within one row. Therefore, the only thing that matters are the last 2 digits. So we ignore the 7, and we look at 2 digits again. Right? So instead of 700, you just strike it out. You just say 0, 2-digit number, right? So 10, 20, 30, 40, 50, 60, 0, etc. Right? And this was when you were 700, right? Now you keep counting. How many steps you need to take before you get to 60, right? So you keep counting 60 steps. Now you know this is your home, basically. You're going to get there. So 60. Well, call, yeah, mercifully. 1. 6. 1 was. This is the explicit display of place value. So we know this is true. Right. Now, the equal sign is used very carefully, right? This is actually true. I'm landing at the same number. So, equal. This is called the expanded form. It tells you, now when you look at this, you no longer need to emphasize, oh, the 5 is 5,760. It's right there. You don't see you're in trouble, right? That's what it is. That's not good enough. I'll tell you in a minute why it's not good enough. Right? Oh, very hard. That's not good enough. What reason? Well, for one reason. Suppose I give you a number, which is something like this. I'm making it up as I go along, right? Okay. So you want to write it in the expanded form. What do you say? 8. Sorry. You scramble. God, forget it. And so on, right? And then that's 5, and so they say you count again. Don't you feel dumb?
Yep.
No, 7. See, that's the trouble. That's the trouble, right? Right there, you see the trouble, right? You lose track. 7. Then plus 1, 7 is tolerable. That's it.
What about the 1?
Oh, I forgot the 1. Just erase it. By common consent. That's democracy. Now you know this is not the way to live, right? So we have to do better. That's what the exponential notation comes in. I guess as I explained to you, we do it not because it's fun, but because this is necessity. So to do that, let's observe something that's so. Forget my exponential notation. Let's back have a look at just honest meaning of addition. So now, watch. This is very carefully orchestrated. If k is a single-digit number, then k times this is the number k 0, 0, n. In other words, 8 times 1 Now let me see if you believe this. Do you believe it? Single digit. Now that's the whole difference. I'm not saying anything fancy. Take 8, take 5, whatever. Now look at this. You believe this? Believe this, right? Because what's there not to believe? You look at this total display of 51 digit numbers row by row. Right? 8 times it means what? Starting with 0, you count 8 times down the rows, right? You can. Well, of course, you land at 8,000. There's nothing not to believe. Strictly counting, right? For single digit numbers, there's no reason for you not to believe this. So this is true. Good? But this also means what? As a consequence, right? Knowing that we already established a theorem for this, right? 1 followed by k zeros, we can write it much better. Namely, what? Oh, I don't dare write too hard. Can you read? Is it readable? Oh, no, sorry. Good? Yeah? So every time you see a funny, what do we call a number like this, single digits followed by so many zeros, now you know. Can be much more compactly written like this, and this because this saves the effort of this curly bracket and so on. All right. So for the case at hand, that means what? That means I can rewrite this. See? Now you read it backwards. Oh wow! Actually, this is straightforward. 5000 is what? In this notation, it becomes what?
5 times 10 to the 3rd.
10 to the 3. 7 times 10 squared. 6 and 10 plus 1. Okay. There are always little nagging tidbits that you probably don't like it, but you have to take care of. So here, come to here, then you see something funny. See? It's coming down, right? Clearly, the exponent. Oh, that's called exponent. You all know that, right? This 3, 2 should be 1, and it is because our definition is what? 10 times 10 to the n, n times is equal to 1 followed by n zeros, right? If n equal to 1, 10 is, n equal to 1 means 10, right? N equal to 1, that means it's only one factor, no, whatever, sorry.
Yeah.
No, 10 to the n, sorry.
Yeah.
Sorry. That's our definition, right? So if n equal to 1, that means 10 to the 1 is exactly 10. So that takes care of that one. So even though I don't write it, which is, you don't write it just because why do you add work yourself? Everybody understands that just one, so leave it alone. But if you're still on this kick of seeing the exponents coming down, so you what? 3, 2, 1,
0.
should have 0, right? You should have, so in the best of all possible worlds, you ought to have this. At the moment, you don't. So you insist. That's your definition. It's one of those things that you just tap on because it makes things look nicer. Again, I mean, you'll be crazy if you write this all the time, right? Who wants to know about this? Nobody. 1 is 1. It's good enough, right? So normally we don't do this. But just for your ease of mind that we're doing things as reasonably as possible. I'm just proving to you that can be done. And we don't do this, and we don't add the 1 either. So it's just, normally we just write this. Normally. Okay? Now that is satisfactory. This is entirely satisfactory as a statement about place value. Because why? You have eliminated completely this guessing issue. What is 5? It says it corresponds to the power of 10. Now coming to that horrible number, right? What did we have? 8 something, right? We just make it up again. And we can write it very convincingly. Alright, 8 something, something, something. Alright, I just want to make it up all over again. Was it 5? Oh, doesn't matter. Okay. So then I write the expanded form of it. 8. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. 5. Nobody can complain about this. No need to count anymore. Once you've written it, in the future, you have any doubts what it says? That's the whole point about both brevity and clarity. Right? Those are the main purposes of having symbolic notation. Okay? So this exhibits place value like nobody's business, right? What is 8? You know 8, it tells you 8 is not 8, but rather it's 8 times 14 zeros. This is 5 times 7 zeros, and so on. Now this is expanded form. So I keep the best after you come back from the break. In other words, now we get this expansion. Okay.